Hello and welcome to the module Load Data Calibration. So in this module we'll see how important is a load for a robot, a huge robot mostly. So by now you have gone through dynamics in which you are already familiar with equation of motion of a robot and you have seen how that is a function of mass and moment of inertia. So you have already gone through trajectory and position control of any robot, especially robot joint. You have seen how joint motion can be controlled. Okay, and you have also seen how sensitive it was for the masses which are involved and for moment of inertia if it is there. Okay, so in this module we'll see how load is to be communicated to the robot itself. So let us continue with our lecture today, that is on payload and supplementary load calibration. So yes, we are going to cover in this module our payload and supplementary load calibration. That is today's lecture that we are going to do. And identification experiments, that is again for the same reason we are doing identification also in order to identify the moments that are going to come due to any static masses if they are there. So that is to identify the static moments basically, that is only due to the slow motion of the robot if it is making. Okay, and we'll do that using torque and the joint angle data by making different kinds of motion. We'll see very much in detail in this. And the last lecture will continue with repeatability test, that is ISO 9283. That is one of the most important parameter which is mentioned in the robot's specification you have seen. That is, so this ISO 9283 standard, especially it deals with the manipulating industrial robots. It deals with performance criteria and related test methods. We'll discuss various test methods in this. What are the environmental conditions it should be there, and how the robot is to be tested for repeatability and those things. Okay, so let us continue with payload and supplementary load calibration. That is today's lecture. Okay, so let me just introduce you to load data calibration, why that is important, how that is done, so on and so forth. So it makes the dynamic model of the robot more precise. You saw your dynamic equation of motion, it looked like this. I torque is equal to I theta double dot. Everything is vector out here. Those are a few matrices. This is matrix. Tau is equal to I theta double dot plus C theta. Theta dot, it is function of theta and theta dot. And then you have gravity compensation torque, that is only function of theta. So you see inertia term is there and it is a significant term. It carries huge amount of value and it contributes a lot to the torque which is going to come at the joint. And same if the robot is moving at a good velocity, you will also see velocity also affects the torque. So this is the contribution due to centripetal and Coriolis effect. That is again a function of mass also. So there are masses of the links that goes here. This is the velocity which comes here. If velocity is significant, this term becomes quite significant. So also in case the robot is not moving, knowing the mass is also very important, because this is the gravity component. When you see torque, the contribution of this element to the torque that holds the robot in its place. Okay, or it just moves in a slow velocity. Okay, so these are the terms. So you see there are plenty good amount of contribution of moment of inertia and masses to this torque. So knowing these values more precisely will help you to communicate your controller about your robot itself, because the controller runs in a closed loop. So it also continuously tracks the errors which are there in the trajectory. So quite a lot of time there are model based control in which you use this particular model of your industrial robot to feed forward your robot with that torque and then check the errors and use some gains to control the robot more precisely. So that is what is used in most of the industrial robots. So in this case, the dynamic model is more refined. If you put the values of moment of inertia and the masses, your dynamic model becomes much more refined in that case. Okay, so model based trajectory control is for complex motion profile. You have seen earlier in our application videos when I've showed you a robot is doing a gluing operation. It was moving in a free form shape and it was doing that gluing operation. There are painting operation also, that also the trajectory is very complex, and in case of laser cutting you have seen. So there are many applications in the industry in which your robot makes a complex motion. Okay, and trajectories are there. It is not just path which is important, it is trajectory also which is important. That means each and every point you have a fixed set of joint angles and the Cartesian values of its end effector. So those points are not just freely stated in the space, they are to be there in a manner when time is also varying, right? So each and every point, the point where it is defined with respect to the time. So that is why your acceleration profile is important, your velocity profile is important. So everything becomes very critical in that case when trajectory is there. So model based trajectory control, and that is for complex motion profile, you need moment of inertia and your masses which are there in different components. They are very important. Okay, so the controller plans the optimal motions using correct dynamic model which calculates the time optimized motions. So it calculates the time optimized motion. So that enables close acceleration adaptation also. If you have considered a motion, let's say you have taken a motion profile for your joint, so it will closely match with the accelerations which are there at different instance of time along this motion profile which is chosen. Okay, so having your dynamic model correctly defined, it makes your controller more closely track this trajectory for the joint, as well as that results in the good trajectory following of the end effector also. This prevents any mechanical overloading of the robot. Let's say you have no idea, you just considered this one. Let's say you have I theta double dot for the torque which is coming here. Forget about the rest of the term. If this robot is moving at a huge velocity and acceleration, you see this creates a torque which is here, apart from what is going to come due to the gravity component only. Okay, so there are torque which comes due to this motion. So this, if this is not precisely known, let us say we know it but not to the actual value, and actual value is much more higher when it is actually moving. Okay, in that case that would cause more amount of torque that comes into the mechanical system, especially your links, your gear units, your bearings, each and every thing which are there in your system. Whole of the mechanical system may get overloaded, right? Right from the foundation to the joint which comes at the end. Okay, so whole of the system is at stress in that case. So you can prevent that using precise knowledge of your system, moment of inertia and your masses which are there, right? So that is to be done. And it also prevents any electrical overloading. If you are your system is loaded with huge amount of torque, okay, unknown torque, basically known is only thing which is going to come because of the mass and moment of inertia of the links, but you also have added supplementary loads, you also have additional attachments at the end, that is the tip of your robot, your end effector maybe. So those are also going to create some torque. So that additional torque I am talking about, not the link and joint torques only. Okay, that prevents electrical overloading also. If you know that precisely, it will prevent any electrical overloading. That means all the motions, all the torques, all the currents which are going to come, you know it well. Okay, so while moving along the trajectory, the controller will calculate currents which should be flowing at that moment of time more precisely. okay, so that you don't get overloaded. Your load data basically comprises of two things. First is the static load, which is only because of the masses which are there, and the location of center of gravity. Got it? So that is going to create moment, static moment. You have seen it in case of statics, the gravity compensation torque which is going to come at the joints. Okay, that was calculated only due to the link masses, but there are masses which are overrun to the robot. Okay, like supplementary loads to different links. We'll talk about that. Okay, so those masses are also going to create some static moment. So mass and center of gravity location of those masses are to be known for static load calculation also. Okay, you also have dynamic load which are going to come, that is due to the mass moment of inertia of any added loads. Okay, this excludes the links, because model of the link, moment of inertia of the link, masses of the link are already fed by the manufacturer to the controller. Okay, so that is, this data is already there with the robot. You have to find out how much is this. Got it? What if you don't do this? The robot must not be operated with incorrect data. Failure to observe this may result in considerable damage to the robot, you see. It affects the service life of your robot. If gears are loaded more than required, there will be more wear and tear that is there in the gearboxes, in the bearings. Okay, it can also cause considerable damage to the environment which are around. Okay, the objects which are lying around. Why? If the robot fails, it may hit the surrounding also. If it fails considerably, in that case, it can also injure a human who are around, who are working along with the robot. Okay, maybe he is programming, he is handling the robots and systems. So that is what. So it is a warning which is placed in any robot manual. Okay, so this is a prerequisite. Before you put your robot to use, you have to do this task, that is load data calibration. So yes, there are procedures for load data calibration, and there are some limitations also. We'll discuss about that. So this process is done by carrying out cyclic joint motions, V path or the pendulum path motions. They are commonly known as V path or pendulum motion in different robot terminologies, with the payload. Payload is already there, and loads mounted on the robot link. Those are the supplementary loads. Along with all those loads, you have the robot controller, or you yourself can move the robot in cyclic manner and observe the torque, note it down, and then you can calculate how much are those payloads or how much are those supplementary loads. A robot can do it with automated programs which are there, which are supplied along with the robot, or it comes as a add-in plug-in to the robot controller software. Okay, so the robot is kept in the working temperature while carrying out the load data calibration. Robot should be in its working temperature only. You know that also affects the torque, because the viscosity, the damping which is there at the joint, that may change, your density of the object changes. So having that in correct working temperature will let the robot know your dynamic model more precisely when it is actually working. So you have to take very much closer to that. There are procedures which are there in the robot which are known as warming up procedures also. So before you perform this test, you have to do warming up procedure. Okay, so the range of axis motions are different for each joint. That is done if it is automatically done by the robot. With the bigger links moving at a smaller angle, that much should be enough, because a bigger link, even if it moves by smaller amount, it gives sufficient amount of data in order to calculate any supplementary loads. Okay, normally axis 1 and 4 are not moved. You see, your axis 1 was the perpendicular to the ground motion. Okay, if your robot is like this, this was your axis 1. Okay, and then you have axis 2 which was here, we have axis 3 which was here, and you had axis 4 which was moving your spherical center, wrist center, about this axis, about this axis. You see, moving this doesn't cause much change in the current. Okay, moving about axis 4, even if you have a payload, it hardly changes much of the torque which is going to come at different joints. So that is the reason this is not much moved. Even axis 1, because it is moving, normally they move at very slow speed, and even if it moves, it is moving not against the gravity. So the torque variation is not much because of this. So these are the reason why this is not used while identifying the load data. Okay, so few robots, they use this motion also in order to find out the moment of inertia, but definitely not due to not while calculating the static load. So yes, the controller records the currents that results from the joint axis torque while it is moving. Okay, the complete profile of the joint torque and the current, joint angular position and velocity corresponding to the time is recorded. Okay, so that means it wants to make this equation once again, C theta, theta dot and gamma theta. So it is going to use whole of this equation and want to calculate using the precise measured joint position and velocity, feed it here, and it will check how much is the error in torque that is going to come. Iteratively, using that, it will calculate all the moment of inertia and the masses. Okay, these data are used as a basis for calculating the load torque, okay, and the load data. The load data can be obtained using manufacturer's information also. If you have attached any supplementary load, you have complete information about its center of gravity, its moment of inertia and shape and size. You can put that directly to the robot controller through numerical inputs in its teach pendant, or by manual calculation. If you could do it, you can calculate and you can put that. So there are procedures, you know how to calculate equivalent moment using the moments where does your actual center of gravity location lies for set of bodies, or same way you can calculate for set of bodies where does your moment, how much is your moment of inertia resulting out of combination of multiple known bodies. If you have a CAD software, or by doing some external measurement experiments to find out that. So these are the ways how you can load the load data for your added masses. Okay, and these can be done automatically using dedicated softwares if you have that provided by the manufacturers also. With almost 5 to 10% variation, it can do very closely, but normally this can only be used for payloads only, not for the supplementary loads, and over 20% of the rated payload. So supplementary load can be almost around 20% of the rated payload. So these are some of the limitations what I have told. So when I am using an automatic method to identify my loads, okay, so there are error to that. They are not very the close value that you can obtain. Closer one if you know the system properly through these informations. Okay. Okay, so the optimum start position for a floor mounted robot for automatic identification is the cannon position. You already know that. I'll show you a video now that will show this cannon position more properly. So for that, axis 1, 2, 3, 4, 5, 6 for a 6 degree of freedom robot is like this. It is nothing but it is something like this. Okay, you have, this is the ground frame and robot stays in at least this position. Okay, so let me just show you a small set of demonstration video, okay, in which there is an application which is put to the robot controller, and that allows me, this is for Yaskawa GP12 robot. So you see it is something like this, in which you have to start like this. This is the front screen of the teach pendant I have captured. Okay, and in the next case I have just used the tool coordinate system which is to be taken. There are multiple number of tools which can be attached to the robot. and they can be taught. You have already seen in case of TCP calibration. So you have multiple number of tools that you can have. You have to select the proper tool here. Okay. Once that is done, okay, this is the blank data which is shown here. This is the blank data. You see everything is 0, 0, 0. So the values which are here, you see, this is nothing but 0, 0, 0 and 0, 0, 0. This comes from the TCP calibration. That is the offset of the tool center point from the flange. So this is the data which comes from there. Okay. This is the weight of that. This is to be identified, and the location of center of gravity is to come here. This is the moment of inertia which is to be fed here. Okay, it can be done manually, but now this robot will do it through its automatic code. Okay, you see this is all star, star, star. Now it is asking me to consider the added mass if it is there in this, because now I am going to perform tool calibration, tool load calibration. Okay, so it is also asking whether to consider any additional load if it is there on the U arm. So it may be considered or it may not be considered. Okay, so if I select consider, so it does some sort of motion for the home position. So now let me show you the video. So robot it comes to the cannon position first. Okay, then it will do a sequence of motion and it will try to find out everything. So XG, YZ, ZZ is found out by the first motion. Let me just run the video now. Okay, so this is the initial position where I started. It gradually went to the cannon position. Okay, as soon as it came here, it did some small motions. Okay, to find out that is the XG, YZ, ZZ position was found out. So two different angles is required. One is like this, another one is like this. Okay, that is it is probably trying to calculate the moment which is come due to the gravity. So how is it calculating the moments? It is based on the current data which is there in the motor of your robot. Okay, so that motor, using that current data you can calculate the torque. So it is using, because it has no implicit torque sensor at the joints, so it basically calculates everything based on the current data, and that is the reason why it is not very accurate. So now it is trying to find out the moment of inertia as well. Okay, with this motion, what you can see now, so it will take it to the home position once again, and it will find out all the moment of inertia, Ix, Iy, and again by making some other motion, it will try to find out the moment of inertia about Z also. Okay, and finally it takes you to all the values. You see, because this gripper is almost slender and it doesn't have much of a mass distribution along Z, so it took it as 0, 0 now, but it could precisely find out the center of gravity location which you can see here, and the moment of inertia about X and about Y. Because it is very extended link along X and Y, it can calculate that. You see, and this data what you see as 0, 0, 0, that will come directly from the TCP calibration. Okay, so normally the TCP calibration as well as this load calibration, that comes together in a single menu. Okay, so this is how it is done automatically by the robot. If you know your system well, that means you have full knowledge through CAD or through manufacturer data or through experiments that we have discussed, you can directly feed in here. Okay, that will be much accurate as compared to this automatic calculation. Now, where are the reference frame? Okay, how it has actually stated those mass location. Okay, those are the loads that comes onto the robot links and the payload. Okay, the payload on the tool flange is defined in the tool frame. So if there is tool frame, so the payload which comes after this tool frame anywhere over here, so that can be calculated based on the frame which is attached here. Okay, so any displacement will be mentioned with respect to the frame which is attached over here. That is the tool frame. So in those cases, what could be your payload? Payload can be your tool. Anything that comes after your flange is your payload. Okay, so robot, when it is delivered, if it says it is 12 kg payload robot, it is with nothing. Okay, it should not have any tool. It doesn't have any sensors, adapters or anything. So these could be your payload. This all comes under your payload. Adapter, camera, gripper, okay, and the mass that you are actually carrying. If it is a gripper, it can pick up something. So that also is a payload. Overall, the payload is the sum of everything which is attached after this flange. Okay, so that is the payload. We have already seen it when we were discussing about the technical specifications of the robot. So this is your payload and it is defined with respect to the frame which comes here. Okay, this is the flange, robot flange which is there. Okay, it is commonly known as tool flange. And then you have supplementary load on the links 1 and 2. So this is your link 1. Okay, and you have link 2 which is here. Got it? So link 2, and these loads which comes here are defined with respect to the base frame. That means when it is defined with respect to this. Although this link is moving, that means you have to bring your robot to this cannon frame. This is the cannon position of the robot. So in this cannon position only, this is defined. Okay. So common load that comes to these two links are transformer, it can be power supply, any heavier load should come on these two links. It should not come somewhere over here. Got it? That is on the link 3. Okay, the link 3 should have only the smaller load. Okay, and there are many a times it can be a compensating load. Sometimes you have huge payload which is there. You can have a compensating load also here, which has not much of a function other than compensating the load which comes here. Okay, so that is supplementary load that comes on link 1 and 2. Okay, link 3 is commonly defined in the tool frame. So because it moves along with this, okay, this link that includes axis 4, 5 and 6. Okay, so link 3, whatever comes on the link 3 is defined with respect to the frame that comes here, that is the tool frame. Okay, the common inclusions are for that load is valve block, welding accessories, pneumatic valve blocks, correct, cabinets, counterweights also can be there as I have told just now. Okay, and all loads added together gives the overall load that is going to come on the robot. So whole of the load should be summed together. Okay, typical joint angles for defining this location, this is the cannon position which is defined here, is this one. Got it? Okay. Now the effect of load on the robot. So if it is only the payload, this is given even in your data sheet. So where can it lie, how it should be. So you see it is defined with respect to the, this is the center of gravity location of the payload which is there. It is defined with respect to the tool flange which is there. Okay, with respect to the tool flange. So this is the X offset and Z offset and Y offset. So all three together will take it to this location. So this location is defined precisely with respect to the tool flange which is here. Okay, and the influence what it can do is, you see if you are within this region, so this is LZ, how much far away it is along this direction. This is your Z axis, so that comes here. So whatever is this, so if you take it more along this, so if it is a 5 kg payload capacity robot, I have taken it from KUKA KR5 ARC robot datasheet. So till here it can manage with 5 kg payload. Okay, if you take it further away after this much of distance along Z, your payload gets reduced. You can carry less load in this case. It is 4.5 kg, and then you can carry 4 kg, 3.5 kg, 3 kg, 2.5 and 2 kgs. You see, the farther you go, same weight, same load is going to create more amount of torque. Okay, if you go further, torque gets increased, which actually comes to the joint which is there. Okay, so that is the reason you are limited by, because you are limited by the torque which this joint can handle. So you are limited by the moment you are going to handle, and same way the weight, it gets reduced if it goes farther away, right? And it is there also along xy. So this is the xy distance which is here, and that is mentioned here. So if you increase along xy, again you see you have less amount of load that you can carry. This is the static load calculation only. Okay, this is what is given in your data sheet, but dynamic load will be even less. Okay, so that also depends on the shape of your object, not just the center of gravity location, also depends on the shape of your object. So that cannot be so easily defined. So that in order to do that, robot has to make some motion also, because those are the dynamic torques. You have to find out the moment of inertia. Got it? Okay, so static overloading and dynamic overloading, what it is? So static overloading are the maximum permissible motor holding torques and the gear torques. If that gets exceeded, it is known as static overloading. So this can be prevented by reducing the mass and thereby the weight of the load that is going to come. Okay, shifting the position of payload center of gravity towards the flange center point. You have seen it just now through the table which I have shown you, through the figure which I have shown you, this one. Okay, so you have to reduce that offset distance from the flange which is there, or you can use the higher capacity robot. That is not always in our hand. Once you have selected a robot, you have to prevent any overload that is going to come to that. Okay, again dynamic overloading. The load data is more than the recommended specification, and that can only be found by doing some tests. Tests are done using the test software that suggests the percentage of load on each axis by the test that the software performs. Okay, in case of industrial robots, you cannot check the torques very precisely. You cannot even know that current which is going to flow by moving a load, right? It doesn't give you much of an access to those parameters. In that case, you have to depend on the software only, which is provided along with the robot, and more so the mathematics that goes behind. That includes quite complex electromechanical model. That doesn't mean it goes beyond the scope of any user, but that can be done only with the available data which you have. So you have to depend on the test software. But in case of research robot, that can run on torque control, and that allows you checking the torque at the joint and current precisely while it is running, then you can do further experiments. We'll discuss that later in next lecture only. So that is what we are going to do in next lecture. Okay, so this can be prevented by reducing the moment of inertia. How that can be done? By reducing the mass distribution, reducing the mass, or using geometrically compact load. This effectively reduces the distribution of mass. Okay, it is making all the masses which is distributed in the volume coming very closer to the axis of rotation. Okay, so this is what is to be done, and using the robot of higher payload capacity. Again, this is not in our control all the time. Okay, please note, after load calibration also, any existing codes, if you have already done some programming of your robot to perform, let's say, welding task, if you have done this load calibration, you have to redo that programming, or you have to check the accuracy of the motion if it is doing. If you have made it go with 2 mm gap throughout the trajectory from the surface, okay, so that 2 mm gap may not retain as it is after the load calibration. Okay, you have to redo that and check the quality of the trajectory following. Okay, so this is to be noted. Again, a more generic approach that uses a torque controlled robot is discussed in my next lecture, which I'll be doing, that uses a standard industrial robot, but I have an access to its motor current. So using that, I'll discuss how to find out the load data as well, okay, and how to compensate for that. So that is what I'll be doing in my next lecture. So for this lecture, we are done. That's all. Thanks a lot.